So good afternoon, everyone. So our speaker for this Minerva seminar today is Ingo Waldmann. So Ingo is an associate professor at University College London and an Turing fellow at Alan Turing Institute. He's working on extrasolar planet characterization, and in particular in the data analysis and atmospheric modeling of exoplanet atmospheres. And Ingo is a PI of the Exo-AI project, which aims to explore the use of machine learning and deep learning in the data analysis and the interpretation of exoplanetary data. And so today, Ingo will present his work on deep learning in exoplanet characterization. So Ingo, the floor is yours.
Thank you. Thank you very much for having me. Is this recorded? Do you want to press record? Right. So thank you very much for the opportunity. Yes, and the introduction. So I'm from UCL in London, and given this isn't necessarily an exoplanet crowd, so it will be exoplanet related, but I think there's more general points I want to make on sort of explainable AI in astronomy generally. Good. So just to give you a small overview of where we are with extrasolar planets. So, first planet really detected was in the mid-90s, 51 Pegasi b, which more recently got a Nobel Prize for that, and since then it's really been a pretty, for most of the last 2 decades, pretty exponential growth of detecting planets and confirming planets in our local Milky Way. There's been a bit of a hiatus with COVID. You can actually see the cumulative sum here dropping off slightly, but I'm pretty sure that we'll go back into exponential growth, especially also with the next Gaia release, which we will have probably an estimated 10,000 or more astronomically observed planets as a byproduct of the Gaia pipeline. And of course we've got other missions such as TESS mission, which is extremely successful in finding these extrasolar planets pretty much everywhere. So this is very good news. So we're really entering into in the era of big data in extrasolar planets. We've got petabytes of light curves lying around, and large number statistics now are becoming a more frequent occurrence. Just to give you a bit more of a brief overview of what the planet population actually looks like, because it's quite a heterogeneous population. So, and it really depends on the detection technique that you're using to detect those planets. So here in the I hope you can see my cursor in the top left, you've got the transits detected from the planet passing in front of the star, obscuring some of the stellar lights, and these are the ground-based detections. Then the Kepler Space Telescope also has a higher sensitivity, and detected more. But as you can see, all these planets are pretty close into the host star, so the 10th or 100th of an AU. From its host star, and this is mainly because it's easier to detect high frequency occurrences in time series of these transits. So it's a selection bias, but also what you can see is that a lot of these planets are quite big as well. So they are Jupiter-sized planets because again it's easier to detect a larger planet. But then you've got the radial velocity as well as ways you measure the Doppler shift of the host star due to the planet's gravity influence, and you can get a bit further out in terms of semi-major axis. Again, large planets, but with micro lensing and others, we can actually start going down to the regime of Earth-sized planets. So this is our solar system down here, which is not very well populated at the moment on this diagram, but again, it's a bit of a selection bias. And then on the top right, you've got direct imaging planets. So these are self-luminous planets that are still hot from the recent formation. So these are young planets. and you can detect them directly with GPI or Sphere, for example, on the very large telescopes. So we've got quite a dichotomy here, and the field is really quite split in different sub-communities, and different techniques used have different applications of machine learning. Some of them are time series based, and some of them, for example, are image based, and some deal with spectroscopic measurements. So it's quite a heterogeneous field. So it's quite different. So, for example, if you look at cosmology measurements and Planck data, for example, where we've got one very good data set here, we've got very different issues with different data sets. But we are really entering the era of very dedicated studies of exoplanets, and these are just some of the space missions that are involved in this study. And of course, here James Webb has now launched and deployed very successfully, and it all seems to be going to plan. So this is fantastic, and James Webb will really revolutionize our understanding of atmospheres of exoplanets, as it will have a significantly higher signal to noise and wavelength range. And then later on in the decade, we have the Plato mission, so 2028 or 27 launch, and then an aerial mission, which will look at 1,000 exoplanets, and it will characterize the atmosphere of these planets, to be launched in 2029. So that will really give us a broad statistical overview of characterization of these atmospheres. James Webb will do a few of them, but in the order of tens of planets, whilst aerial will do aiming to do 1,000. So what's the state of play? I mean, given all these missions and given all this amazing data coming in, what's the state of play of machine learning in exoplanets at the moment? So it's still very new to the field. So compared to radioastronomy or cosmology, for example, we are, I think, a little bit behind. But it's picking up very quickly. So since for the last 2 years, it's been a dramatic increase in papers. And if you actually search for AI in exoplanets on the different papers that are on ADS, you get this sort of diagram out here where it boils down to most of the papers are actually addressing areas of high data throughput. So direct imaging, for example, with GPI and Sphere, we have loads of data coming in, and SpecSAO and all these fantastic instruments. So you expect machine learning applications to be where the data is. Same with transits as well, with our transit surveys. So this is time series analysis. But interestingly enough, you have quite a lot of stuff coming up on atmospheric transmission models, and actually trying to build surrogate models for very complex atmospheric forward models that are very, very slow to run at the moment. And this is where I specialize in, and this is where I will spend quite a lot of the talk on. And then other smaller topics, microlensing and radial velocity, for example, have had some applications, but comparatively few compared to these three main topics at the moment. So what are the main challenges in exoplanets? Well, you will, even if you don't know anything about exoplanets, you will quite easily recognize some of these issues here, because they're prevalent to most data analysis in astronomy. And some of it is rare event anomaly detection, for example. So this is the prototypical case is finding a transit in a noisy time series, and transit is just a bip in that time series. Then you have complex time evolution. So, for example, stellar noise or instrument noise. So you have a very complex autocorrelation function, which may be heteroscedastic and over some periods. So you can really have a lot of noise in your time series measurement, which makes the anomaly detection that much harder. Then, of course, you have multiple signals convolved on top of each other. So you have the stellar noise as much as you have the instrument noise. With stellar noise, I mean stellar activity. To us, it's noise. To others, it's science. and the planet signal, which is what we are interested in. Then of course you've got severe class imbalance, because you look at 1,000 stars and only a small percentage of them will have planets that are detectable with a transit method, for example. So you're statistically incomplete, and quite often you don't have a true negative. So the fact that you're not detecting something doesn't mean it's not there. It might just be that your telescope is not good enough. And domain transference, you train a neural network, for example, on the Kepler mission, and you want to transfer that to the TESS mission, similar sort of data, but very different instrument noise. And this is very, very difficult and proves quite difficult to handle at the moment. And of course, solving the Bayesian inverse problem, which is something that I specialize in more. And trying to go from the observation to a distribution of the parameters for a given forward model, and I'll talk about that in a minute. But so these are all very similar problems to many other domains of science and astronomy. So we're always very keen to collaborate with people who have maybe a slightly different view on an existing challenge. Just to give you a quick definition here of what I call atmospheric retrieval and an inverse modeling process. So traditionally you would get an atmospheric model here, for example, that produces an atmospheric spectrum of a planet that is dependent on X number of parameters, and then you would compare that to the data. And the inverse process is literally, the retrieval is literally the opposite, as you go from the data and trying to work out the distribution of the probability distribution of the parameters. So this is your posterior distribution, if you're talking in a Bayesian sense. So that's, pretty straightforward. And that's, at the moment, it's sort of the state of the art of the field. There are quite a few codes that are now available to do this sort of stuff. If I forgot your favorite code, then please just let me know. I'm trying to be as complete as possible on this list, but I always miss some. And the idea here is that, for example, here you get a typical fit to some exoplanet atmospheric data, where you have the abundance of the trace gases in the atmosphere, water, CO, methane, temperature of the planet, radius of the planet, and so on and so forth. And the issue there is not necessarily that this is particularly difficult to do. You just get a Markov chain Monte Carlo algorithm or nested sampling, or anything similar along those lines. The problem is that the forward model is becoming more and more complex, and especially with James Webb data, it's going to be so demanding that running an iterative fitting process that requires 100,000 iterations or so to converge will just not be possible anymore within the lifetime of the space mission. So that's a real issue. People have done a lot of work on, parallelizing this with GPU support and so on and so forth. But some of the input data, especially the atmospheric line lists on high temperature molecules, are sometimes very terabytes large. So it becomes a HPC issue of quite a different proportion. And the other issue is that you're quite quickly running into what's called the curse of dimensionality, and it's that your atmospheric models become very highly dimensional, because you're fitting a lot of chemistry, you're fitting a lot of the temperature profiles, and accounting for 3D effects in the atmosphere, which is notoriously difficult. And that means that quite often traditional sampling techniques don't really cut it anymore. So this is an example of multi-nest, which is one of the most commonly used samplers, written by Ferros et al. That it runs out of steam, basically, if you're starting to hit the 30 to 50 dimensionality mark here. And the cost of sampling a high dimensional space at that point becomes prohibitively large, and with an exponential increase. So that really puts a ceiling onto what you can do with a traditional sampler, such as nested sampling or multi-nest or so on and so forth. So what do we do then? We do need to solve that, but at the moment we can't solve it traditionally. So can we use AI or machine, AI? It's always called AI on a PowerPoint presentation on GitHub. It's machine learning, but can we use machine learning to solve some of these issues for us by providing a more robust and more intelligent sampling of a high dimensional parameter space, for example? So this is just a sort of infographic we did. You get the information from the planet as the stellar light shines through the atmosphere. You're being observed by a space mission or a ground-based telescope, and then you take that observation, and the machine learning algorithm will give you an estimate of your abundance, water abundance, for example, temperature and cloud pressures, for example, that you can take as an input to a more traditional Markov chain Monte Carlo, or you just run with that if it's accurate enough. I mean, that is the dream scenario. That would be fast, and then it would solve a lot of our issues that we have at the moment. Now, in 2016, we tried something along those lines. So this was the dark ages of deep learning. And this was pre-TensorFlow and pre-PyTorch. So I used Theano to write a deep belief network at the time, which is a sort of fully connected small neural network. And the idea was, we can't do this quantitatively, so can we at least do this qualitatively and look at a spectrum, train it to recognize spectral features, so at least we have a pre-selector to our Monte Carlo sampling routine of what molecules it should include, and cut down our computational costs that way. We at the time had no idea whether that's even doable. It turned out that it works actually really well, and it's an easy enough issue for even simple neural network to address. And at the time so these are the probabilities it gives out of it being, for example, water in this case, which is correct, methane, and even though it wasn't trained on mixtures of molecules, but only single instances, it even correctly identified molecular mixtures in spectra without knowing that it should do that. So that was the first time in the field that we've done something like that, and it looked promising, and we thought it's a good way to go, at least some of the way. At the time, this was big news, and sort of the Daily Mail, which since this is recorded, I'm not going to necessarily say too much about the credibility of the Daily Mail, but but we put out a small press release, and we clearly said this has nothing to do with AI. It's very simple machine learning, and it has nothing to do with aliens. And we called our code robotic analysis of exoplanet retrieval, something like that. And that was the headline on the Daily Mail, that AI hunting aliens. So that was quite funny. It was a lesson learned. And funnily enough, one of their artist impressions was just a humanoid android, thinking about exoplanets and looking at analog folders to work it out. So yes, that was another funny one. Yeah, so that was back in the day. It's improved fortunately, has improved significantly since as a field. And there have been multiple approaches to trying to solve this inverse process of going from an atmospheric spectrum to the actual parameters. One idea we tried in 2018 was, and I'm not going to go into details there, is using generative adversarial networks that have two independent neural networks, a generator and a discriminator, and the generator will have to, generate a good understanding of the data set, but not directly being fed the data set itself, but only through a discriminator, which will give it a positive or negative feedback loop to the generator network. It's quite complicated, and it does suffer mode collapse quite regularly, and so it's not necessarily the most stable, but it is really good at understanding very complex likelihood functions, and it's very good because you don't have to specify your likelihood there. Now, what you get out is an estimate of your abundances, and they're usually quite good, and you can actually see that the real spectrum here is very close to the generated or learned spectrum, so you can give it a small parameter range, small wavelength range, and it can actually impaint the remainder of the spectrum very accurately. So that's fantastic. But one of the issues is that, of course, the parameter ranges it gives out here, these histograms are not formally Bayesian. So that should be, the error bars should be taken with a pinch of salt. Then there were different approaches as well. So also in 2018, 2019, and there's been a few papers since, to use random forests. So random forests are, much older than any of this deep learning stuff, and very well understood and very easy to train. So this is a definite advantage of random forests. They're also easier to interpret, and I'll talk about that in a second. One of the issues with random forests is that it does do very well on an individual data set, but in the instances that we have here, the random forest needs to be retrained every time you want to look at a different planet. So if you always analyze the same planet, that's fine, but if you're actually looking at a different planet, then you have to retrain your network every single time, and at that point it becomes not very scalable. So this is something where deep learning is a bit better on, that you can actually train over a large population of planets, for example. You can technically do that with a random forest as well, but the random forest becomes very, very heavy at that point, and then training costs become quite substantial. So, but that's one approach. Another approach is to use, so this is Kopp-et-al. 2019, ensemble Bayesian network, for example. So you're actually looking at not one neural network, but you're looking at a number of neural networks. And the idea here is that each individual neural network is a weak learner, so it might not get it right, but the ensemble of multiple neural networks will. So it's averaging out its uncertainty in the prediction. So in that sense, it's very similar to random forest, right? So it's, a random forest is just a collection of decision trees, and they're also weak learners by themselves. But if you add them in an ensemble, you're actually getting a more robust measurement. Which is, so this works quite well, but again, the issue is that it can account for its own uncertainty by, you're outputting, instead of an individual parameter value, you're outputting a distribution. In this case, it's a Gaussian distribution by predicting the mean and the sigma, sorry, the sigma here and the mean here. But the issue is that you get a better understanding of the uncertainty of the network, but the network doesn't include formally the noise on the observation on the spectrum itself. So in that sense, it's not a fully Bayesian posterior, because you're not including that error in your loss function. So that's a outstanding issue, which is true with all the techniques that I've shown so far. So this is not unique to that one technique. So to address some of that, Hims et al. Went a completely different way and said, like, well, I don't want to do the full inverse model, but I just want to do a surrogate model of my atmospheric transmission code and use that in a traditional Markov chain Monte Carlo technique. And by just speeding up the forward model, I get the same benefits, but I can actually do this in a formal Bayesian setting. So that actually works very well. But of course, it depends on whether the forward model learns biases induced by the physics correctly. In most cases it does, but not always. But yes, it's a very promising approach, which makes sense. So, but this said, there are still, as I already said, there are a couple of elephants in the room for the field. So a few things that we just don't fundamentally understand until now. So first of all, how did the neural networks learn the physics? You give it an input and output example and a loss function, and you're trying to, then converge your neural network. But what exactly happens during that learning process? Where does it focus on, and what exactly does it learn? Does it learn all of the, intricate covariances between parameters that you get in a complex model like that? Or does it not? Does it just approximate some of them? Does it completely ignore some parameter spaces at all? Are the predictions biased? So this is, and how uncertain are they? So this is important, right? And if you're you're using just models in a sandbox, as in you simulate a forward model, add some error bars, and then you have the neural network retrieve that. That's fine. But how realistic is that in the real world? Because in the real world, you don't have the ground truth, and it's much harder to understand if a systematic noise in your data will lead to certain biases retrieved by the neural network. And this is very, very difficult to understand. And, how complex do these neural networks need to be? I mean, do they need to be, ImageNet level heavy, or do they, just need to be a few layers deep? And sort of what architecture works best? Is a convolutional net better over an LSTM, for example? Or transformer? And the other obvious elephant in the room is like, we do understand the physics. Why are we not just putting the physics in as well to help the neural network? Because as long as you have a deterministic algorithm that you understand, it's always better to use one. Now, part of these questions can be answered by something called explainable AI, and this is really, I like using this slide because it really reminds me of, the journey to the Wizard of Oz, who, is in itself just a big mirage, but, apparently holds the answers to everything. And this is somehow how it feels at the moment, trying to do machine learning in the field. And explainable AI has been extremely popular in the fundamental AI world over the last couple of years. So it's really started coming up from 2018 onwards. And the number of papers on explainable AI is exponentially increasing. So you have several thousands at the moment. So it's a bit hard to catch up on. But there are, fortunately, quite a few good review papers of the last year, or the last 2 years, really. And just to give you an idea of how much work there is at the moment, is that there's a review paper of review papers, and not only just one, but several. So, I guess it's a meta review at that point. I'm not sure. But there's a fundamental need, of course, not only by exoplanets or the physical sciences, but generally by the machine learning community, to understand the reasoning of these black box deep learning models. And as soon as you're being able to explain some of the reasoning behind these models, it becomes easier to trust them or use them in a more effective or scientific approach. So this is a good infographic here by Redo Arieta et al., which is a fantastic paper. So I really recommend reading that if you have time. It's about 80 pages long, but it's very, very good overview. And then there are different aspects to explainable AI. So I'm only going to talk about 3 of them, which are most relevant to exoplanets / astronomy. So local explanations is one of them. So what happens if the prediction of your output, if you slightly change your input? So if, for example, if you slightly wiggle a spectral point in your exoplanet spectrum at a certain wavelength, how much will that affect your measurement of the water abundance of the atmosphere, for example? So it's a perturbation-based inquiry. Then feature relevance is quite similar. Feature which goes backwards and it's tries to back propagate by I have water detected as an output. Can I back propagate through my network to show me what inputs led to that decision? So that's a feature relevance. So this is quite often done, for example, for random forests traditionally. Visualization is a very useful one if you can. So does the internal state of the neural network allow you to make physical assumptions about its output? So can you enforce or demonstrate a clustering of the internal neurons or the internal latent variable space that determines what the output is given the input? It's not always the case, but sometimes it is, and sometimes you can enforce that, especially with variational autoencoders. You can explicitly enforce that, and that allows some physical representation of the inside of the neural network, which gives you an idea of where it's coming from and where the boundary issues are. Now, as I said, there are many approaches to explainable AI, and this is just a small chart on some of the key papers and approaches. So if you have a model agnostic approach, simplifying your machine learning algorithm using simpler decision trees that are more easily interpretable is one way forward of understanding the reasoning process behind feature relevance, as I said. So looking at Shapley numbers, for example, and which sensitivity to input fluctuations, local explanations. Text classification is not necessarily that useful to us, but not in natural language processing, for example, it might be able to explain why it chose that sentence in verbose form. And again, visual explanations very similar to feature relevance, sort of saliency maps and Shapley plots and so on and so forth. And similar to here, so ensemble learning, looking at what the ensemble actually tells us. Can we take out certain ensemble members of the ensemble? Does what's the variance if we do that? Sort of jackboot stripping, for example. Yeah, modifying the architecture of the neural network. How sensitive is your output to the actual architecture, or is it architecture agnostic to a certain degree? What does that mean? So this sort of goes also in a sort of hyperparameter estimation sort of world at that point. Yeah, so there are loads of different approaches, and there is no single answer to making a neural network or machine learning algorithm explainable, but it really depends on your specific application and your specific problem, which obviously, of course, makes the whole thing even messier. But that's what it is. Zhang et al. Gave a slightly different approach to defining explainability into sort of their 3 dimensions, and they say it's 3 things you need to really look out for in characterizing what you can do in terms of making your neural network more explainable. So in the first one, can you actively change your neural network during training to make it more interpretable? As in, are there methods by which, for example, you use a different architecture, like a graphical neural net, to see structures more explicitly? For example, if you model a chemical network, that is useful to do. Or just passively by doing you have your model and you're just varying your input and your output, and then see what happens. Can you have different types of explanations? So giving examples is the least explainable. you know, it will just, the neural network will just output several examples of the same model, for example. How does that change? Can it attribute feature importance, for example, again, to an individual data point that is useful to decision making, and so on and so forth. The best, of course, would be if it can tell you a discrete set of rules by which it operates. So that is not usually useful or available, but for example, for decision trees, it is. And, you know, is your explanation local? You know, is it just pertaining to a small area of your data, or is it global, as in, you know, the global behavior of your neural network over your entire data set? Yeah, so these are things that you need to, you know, bear in mind. And if you're looking for explainable AI solutions, what's actually doable? And you know, there's a nice little chart here on, you know, the trade-off between model accuracy and explainability. So the easier the network is, the easier it, or the algorithm is, the easier it is to explain its reasoning, but also the less generalizable the solution usually will be. So decision trees, for example, are down here because they're quite simplistic, whilst deep learning is, you know, the most opaque, but also has the highest potential. So this is something that, you know, if you're generally starting off trying to do something like this, it's worth bearing in mind where you actually want to end up. What's more important to you? Do you want to understand why exactly it's doing something, or do you want to just, is it more important to get a low variance estimate out, but have a more black box behavior? So this is, you know, design choices. So I was just quickly going to run through, you know, some of these free explainability tools. Random forests, of course, has feature importance built in, pretty much. sklearn, scikit-learn does it out of the box, for example, where it will just give you these feature importance, relative importance maps. So in this case, it's the spectrum analysis here that I showed earlier. And, you know, the importance of, for example, water is mainly where the water band in the Hubble WIFCOM 3 spectral region is, so it's 1.4 microns. So this makes sense. So that is easily interpretable. The way it works is basically, again, so you've got input data here, you feed it into multiple decision trees, they all add up to a common classification, which is just, you know, these color bars here. And if you change, you know, if you change the input somehow, how does the output change, and where does the output change? And that gives you these feature importance maps. So it's relatively simple to understand, really, and it's an effective method to do, and you can do that post hoc analysis. So that's always a plus. Saliency maps are similar. So these are, you know, you go backwards. You've got a label that it outputs. In this case, for example, we used saliency maps to detect planets around stars. So the stars are obscured by a coronagraph, but you can still see some of the stellar speckle noise, they call it, which is just the leaking star noise, stellar flux that leaks through the coronagraph. And that looks very similar to planet signatures. So these are simulated planets, but you can see these are very, very faint. And you can, you know, propagate backwards why it thinks that this is a planet. So these are the heat maps of where it thinks the planet is, and they're always overlapping in our case. So this was a good news. So, you know, from a on-off label, yes, there's a planet, there's no planet, you can actually propagate that backwards through GradCam, for example, is the standard routine here, to propagate the gradient backwards into the image and project that. There are guided propagations as well, so GradCam plus is quite good. Or SmoothGrad, which has been used for recently for galaxy classification. So it's basically to see whether the galaxy is a barred galaxy or not, and then I try to actually also trying to identify how big the bar is, whether you can use it for that. It works to a degree, I must say. I mean, this is what they said in the paper. the idea of a smooth grad cam is very similar to the previous one. It's just that they add a little bit of Gaussian noise to the data in order to prevent gradient collapse. So they're trying to get a mean gradient flow across your network, which makes it more robust to locally learned gradients. Yeah, so that's been used, and it's relatively easy to do in terms of post hoc analysis, and it gives you a lot of information on what it's actually learned and where it thinks features are important for classification. Then the visualization. So this is a astrochemistry example, and I apologize, I forgot the reference here. I can provide that if you just email me. Sorry about that. But the idea here is to use a variational autoencoder to basically, it's two networks, one encoding the data into a Latin variable space, so it's compressed space of lower dimensionality, similar to principal component analysis in a sense. So an autoencoder is just a nonlinear PCA in the first instance. But then you take the variable space to then decompress it, usually through the same network, just in reverse, to get a representation of your data out again. And then you minimize x hat and x, the difference between those, usually with a Kullback-Leibler divergence or something similar. So you basically training that the output is equal to the input, but with a compressed variable space in between. So it's an ideal compression, but often, that variable space doesn't mean much. So, if you have Z1 and Z2, so two parameters in here, that is not interpretable. And what you really want is you want to have interpretable variable spaces where you can really say that, one part of the chemistry falls here, the other part falls there. So if you put X in and you get this variable space out, what chemistry comes out. So this is that you can use this to classify, for example. And they've shown that here experimented with different loss functions, trying to understand the correct one for being able to identify chemically different and chemically identical spectra from each other, and trying to bring those two groups as far apart from each other as possible. So that's one of the best ways of explainability, because it's built in and it's physically motivated, rather than just a sort of post hoc approach. But quite often you can't do that. So going back to exoplanets quickly, so this is just going back to aerial emissions in particular, just to give you an idea. These are the 1,000 targets that we have in the current catalog that we will analyze from 2029 onwards, hopefully. Give you an idea of the spectral range. So this is Hubble at the moment with COM3, so it's very restricted. Aerial will do 1 to 8 microns or 7.8 microns, and then James Webb will do 1 to realistically 10 microns. Of course, he'll go into further infrared, but for transmission spectroscopy, that's not so relevant. So you can see that the data quality will be significantly better to what we have at the moment. So understanding the deep behavior of these is quite difficult, and that hasn't really been done. So quite often in the papers published, you see these plots of predicted parameter versus true parameter, and as long as it falls onto this diagonal line, all is fine. Of course, that is true to an extent, but you can see that there's already structure in here, which is usually being ignored by papers. But the structure is meaningful and actually tells you quite a lot about how the network behaves or reasons. So we wanted to look into that with some more detail, and we also wanted to understand whether these predictions are network dependent, or so dependent on the architecture. What is there a specific deep learning architecture that is better suited for this sort of work on trying to predict abundances from exoplanet spectra? Turns out that it's not really true that there's a preferred architecture. And multi-layer perceptrons, as much as convolutional neural nets or even LSTMs, work just fine. So there's a very negligible difference. So that means that, you know, our problem isn't actually too difficult for deep learning to grasp. So that's very good news. So what we then looked into is, like, you know, what's the bias of these networks? And it turns out that it's slightly counterintuitive initially, but then, you know, if you think about it, it makes some more sense. So here, the right-hand side is high abundance of a molecule, and left-hand side is low abundance. So this is in log space, so 10 to the -6 abundance, for example, for NH3 or so here. And you can see that the biases of the network prediction are the lowest is as when you have a really clear spectral feature, if you have loads of that molecule in the spectrum. And the bias then increases as you drop the abundance, which again also makes sense. It just becomes less certain. But then it starts decreasing again, which is unusual, which was somewhat unexpected initially. And that basically means that there's no more feature of that molecule available. So instead of, you know, staying constant or increasing, what would you expect from a linear model, what it actually does, it just takes a low value that is, you know, just at the edge of not being detectable anymore, and just converges to that rather than anything else. So it's a bit strange, but it makes sense that once the molecule is gone, it's quite certain that it's gone, but it will instead return, instead of, you know, the true value, because it has no access to that true value anymore, because the feature has disappeared, it will select a low value where it still sees some of the feature just about. So there's this behavior which wasn't seen before, and, you know, you can express this in a probability of it being a correct result. You know, we set a random threshold here of 0.7, where there could be anything really, and, you know, it's here you can see the same effect, that the probability of it being correct decreases as the abundance of the molecule decreases in the spectrum, but then it increases again because it just knows it's definitely not there. But these are arbitrary values at this point, so this is something that needs to be kept in mind. And then we're like, okay, so does it make sense to train a larger network with more data, or, you know, what's the or a small network with less data, or, you know, a small network with more data? So does that make sense? Because, you know, the common knowledge is that with deep networks, you just need to throw a lot of data at it and keep the network quite complex, and then, you know, everything will be fine. But in fact, that's true, that if you have a complex network and you throw loads of data at it, your bias will generally decrease, but only negligibly. So that means that we actually have a trade-off of complexity required by the network and you know, data. So we don't actually need, quite often, we don't need a very complex network. And in fact, having a complex network will be at some stage detrimental, because there you have these more parameters to train. So you actually need to increase your data input significantly to train these extra parameters, but these are not actually required by the network itself. It's literally just imparting noise on your solution. So there's a negligible improvement, and in most cases, it's actually better to keep the network small, and with that also more interpretable, than, you know, getting into larger networks from the get-go, which is different to, you know, what many papers, including ours, have done in the past. And then, you know, the last thing is like, okay, well, that's interesting, but, you know, does it actually identify the right features, or is it just learning by heart what's required? And so we did the saliency maps using, you know, an algorithm that's similar to Google's deep lift, but, you know, again, it's a perturbation-based algorithm. And here we can see that the brighter spots actually mean that they're more important to the identification of the spectral feature, which is, the ground truth feature is in gray here. So it's high resolution, and then we've been it down to the aerial resolution and do this analysis. So you can see that for CO, these are the two main bands here. It just knows where to look very, very easily. And that makes sense. And that's very good news so far. But then for CH4, for example, it becomes trickier, and it's still doing a very good job. So CH4 is sort of broadband absorber, similar to water, and has loads of features pretty much everywhere. And as you can see, most of these features here overlap with H2O as well. So, but there's one feature, which is the main feature, the new 3 branch at 3.1 micron, which just doesn't overlap with water for once. And it's also the strongest feature. So it prefers to base all of its analysis onto that main feature, which is similar to what a spectroscopist would do if you look at a spectrum and you're just trained to look at identifying spectral features. Similar with clouds. So these are more complex. So what it's trying to do is trying to understand the highest point and the lowest point, and this point here, which is the Rayleigh scattering curve from the optical coming in. That's the lowest point of the atmosphere. This is where the cloud layer usually is detected with aerial. So it's trying to understand the Rayleigh scattering, and it's trying to understand the scale height by measuring the lowest and the highest point. And with that, you can infer some sort of cloud coverage. So, this is quite complex physics, and it has not been taught the physics. It's only seen the physics by example. So it's only seen the spectra and the ground truth parameters. And it worked out that, they are physically connected. These points are physically connected to give you an estimate of clouds, similar with temperature. And that's really good news, because that means that it is possible to understand neural networks in that respect, and that they can actually understand physical relationships by example. One of the problems, though, is here is what's called the blind man and the elephant parable. That localized explanations may never really be enough, or sometimes not be enough, because depending on where you look, you might get a completely different answer, right? So up here, an elephant might appear very different to down there. And unless you look at a holistic picture and a holistic understanding of what your neural network does, you might be misled thinking that it really knows what it's doing. It might not. It might just locally have an approximation to your answer. So one way of solving this, is by adding the physics in, if you can. And that's not always straightforward, and that requires quite a lot of work, but it's, that would be the ultimate dream machine. We've tried this with detrending exoplanet transits. So in this case, you have the blue was the raw data from the Spitzer Space Telescope, and you can see that these variations are due to instrument noise in Spitzer. And then we trained an LSTM, so a long short-term memory algorithm to learn the autocorrelation of the Spitzer noise and then predict it through the transit. What we haven't done, and this, down here is the corrected, and it works really well. What we haven't done in this paper is to actually take into account the most obvious, which is the transit itself. And we know the transit because we know the planet's there, and we know roughly how big it is and when it's happening. So there's a lot of prior knowledge that can be used to actually help the neural network converge. So we did that in a different paper where we translated our physical model into PyTorch to be differentiable. So we've done this with that, and we've done it with our radio transfer now. So we're just about to publish that. And then you can play around with it inside a deep learning architecture. So you can have, all the deterministic inputs that and the deterministic model that you have, predict your physics, and everything else that the physical model can't cope with, like, instrument noise, variability in your data set, whatever not, can be then taken care of by the neural network. So you can physically separate those two things. You can separate the noise component, which needs a non-linear response, which a neural network is perfect for, from your possibly more linear physical model. And that really helps not only explainability significantly, because you can now differentiate between those two, but it also helps your neural network to train much more precisely and quickly. So you know, the learning curve here is mean squared error of predicting the transit depth, and the blue is just a normal neural network trying to do that, and the orange here is the neural network with the transit model inside. So and you can see that, you know, the error on your final network is much lower, and it also converges much quicker. So basically, it doesn't have to be, the neural network doesn't have to concern itself with the complexity of learning the physics anymore, but it can really focus on what is left, which is the correlated noise, and that really helps it to converge much more efficiently. So I think in the interest of time, I think that's it for now. So I think takeaway messages is that there's a lot being done at the moment, and especially also in the fundamental AI field, and understanding how these black box systems work and how they can be employed in a you know, more robust way that is interpretable. But you know, AI is not always a magical solution. If you have a physics model that doesn't need AI, use the physics model. In AI should only really be used if, you know, if the need arises. A hybrid models are a very good way forward, but they're expensive to implement. So, you know, if you're starting a new project, for example, it might be worth bearing in mind, if you're coding in Python anyways, to make sure that, you know, your functional forms are, you know, PyTorch compatible, for example. So that's one way we're approaching our new codes now. And of course, no one can always keep up with, you know, your actual physics research and the AI community, because they are, you know, progressing so quickly. So we need to build really closer interactions between those two, fundamental AI and fundamental physics communities, to be able to drive this efficiently in the next couple of years. So yeah, I think that's it. Thank you very much. And do you have any questions?
Yes, thank you, Ingo, for this very nice overview, and very deep also. So do we have questions from the audience?
All clear.
Yeah, so looks very clear indeed. If there is no question, I have a small question actually. So you presented many methods that can be used to make sure your results are robust and to verify them. Do you see a few way to test also if sometimes your model can be incomplete or wrong, or missing some components, or missing some instrumental systematics? So do you see some of this, can some of this method also can be used also to test, to make sure that your model is actually complete, or to
to a degree, but that's really case dependent. I think I think understanding model complexity is, I think, one of the very tricky issues we have. And, you know, I mean, not AI specific, I think for exoplanets, generally speaking, with James Webb data now coming, and we're used to HST data, and then our models are, you know, very simplistic, because you can't do much with the HST data beyond, you know, very simple atmospheric models. Now with James Webb coming, I think we don't even understand how bad our fits will be, because you know, you have the known unknowns, but then you have the unknown unknowns, and getting an estimate of that is tricky. I mean, you can, approach this, for example, from, some information entropy sort of point of view, but yeah, it's not easy.
Indeed. And so in many of the things that you are doing, you're also putting in instrumental systematics, right? And yeah.
Yeah, I mean, to the best of our knowledge, right? So again, transferability between even the most perfect instrument simulator to the real world is questionable. But that's one of the main issues as well. It's like, how do you how can you be certain that your estimate isn't a biased, your estimate isn't a biased one if you don't know the ground truth? Yeah, so I mean, with a surrogate black box model, it's a tricky endeavor.
Indeed.
Yeah.
Okay, I think we can stop here. If there is no question from the audience, no. Okay. Well, thanks a lot, Ingo, and thanks a lot for everybody to.
Thanks very much for having me. Brilliant.
Thank you.
Have a good day.
Bye. Bye. You too. Bye. Ciao.
Bye. Thank you.
Bye. Bye.